TQFT. So let me just remember from Marco's lecture what is a TQFT. So a TQFT is a braided monoidal functor, and you go from some category of cobordisms to some algebraic category. Okay, and then to a surface you will associate an object in the category, and to a cobordism you will associate a morphism between the objects that you have associated to the surfaces. Now you have to remember that a morphism in a category is not necessarily a function, right, or an application. And indeed, here in our example, morphisms are not functions, but morphisms are bimodules. So what we will assign to a surface is an algebra, which is denoted SH of sigma. S is for stated skein. And to a cobordism between two surfaces, sigma minus and sigma plus, we will associate a bimodule between the algebras corresponding to the surfaces. Okay, and then the source target of this category, so I will explain, but it is a category which is almost the same as Marco's lectures, right? This kind of cobordisms with cylinder boundary. And for the target category, the algebraic category, so it will be a category of bimodules, as you can see, but these bimodules also satisfy interesting properties, which are given by the topological properties of the cobordisms. Yeah, so the plan of the talk is the following. So first I will explain the source category. What three cobordism do we want to consider, and what is the definition of their stated skein spaces? Then I will discuss the algebraic properties of these spaces, and in this way we will discover the properties of the target category. And finally, I will explain also the relation with the Kerler-Lyubashenko TQFT. So here it will be a bit a spoiler for the last lecture by Marco. So I will be a bit fast on what is Kerler-Lyubashenko TQFT because he will explain it more in detail. Okay, so let me describe the categories. So I call it three-cob arc. You will understand why there is arc shortly. For the object, so we consider connected oriented surfaces with one boundary component, so circle boundary component, and on the boundary you have one marked point, okay, which is represented by this big black dot here. And the morphism, so the morphisms are cobordisms, right? So if you have now two surfaces of this kind, sigma minus and sigma plus, you will consider three manifolds M oriented, whose boundary decomposes into these three parts. So the minus part is of course your first surface, sigma minus, okay? The top part here in red is the sigma plus surface, and then you also have cylinder boundary, which is depicted in this green cylinder, okay? And then you require some natural axioms. So of course, the top and bottom boundaries are the surfaces. Then the ds of M is the side boundary, it is the cylinder, and you want that the boundary, the top and bottom boundary intersect on the cylinder at the circle boundary of the surfaces, okay, which is this. And of course, the two surface boundary does not intersect. And moreover, so there is a technical condition which explains the name of the category. We fix an arc. We fix an arc in the side boundary, which goes from one marked point to the other marked point. Okay. So if you remember Marco's lecture, in terms of this category of rectangles, this cobordism, you would draw it like this. So you remember Marco, we had this kind of diagrams with handles, right? And here the cobordism that you see, it is this one. Okay. So this is just the same category. It is just that I draw the cobordism explicitly just to make it easier to see. Okay, now what is the structure of this category? So composition, it is as usual. You will glue along the common surface. Okay. The identity morphism are secant surfaces. So you take a surface sigma and you do the cylinder like this. And again, I draw it in this way because it is more easy to see. Monoidal product, it is a bit harder to see. So monoidal product, first you have two surfaces. So surfaces, you can put them in a bigger disk, right? You can just take a disk, you remove two little disks like this. Okay, you put points here, and you glue your surfaces here and here. Okay, so this is monoidal product at the level of surfaces. And for cobordism, you do the same things, but you glue now in a cylinder. Okay, in a cylinder like this, without cylinder. Okay, You get monoidal product like this. And the monoidal unit is of course the disk. So I think there's a picture for the monoidal product. Yes, another view. So you see you take this disk minus 2 disk, you take cylinder, then you get this picture and you glue your first cobordism here and your second cobordism here. And this is what we call the monoidal product. And of course, cobordisms are up to diffeomorphism. And finally, there is braiding on this category. So braiding, you can imagine it in this way. So you take your two surfaces that you have made monoidal product, okay? So they are in a disk, and you have two pieces, and now you braid them like this, okay? So if you braid these two surfaces, you will get this image here, which is indeed a cobordism from sigma 1 tensor sigma 2 to sigma 2 tensor sigma 1, and it's easy to see that this satisfies the axioms of a braiding. Yeah, in this picture, of course, you have to forget the inner arcs and market points. So all what is dotted, the dotted arcs, you forget them, and the inner market points, you forget them. You only remember the one on the boundary. Okay, so in this way, you get a braided monoidal category, which is the source target for our TQFT. Yeah, so this is, if you forget these arcs and market points, you get exactly the same categories as in Marco's lectures. And this category has been studied by many people, which are listed here. And later we will see what is the main contribution of all these works. So it is that you have basically a presentation of this category by generators and relations, but I will come to this later. Okay, so now we want to define the stated skein space of three cobordism. So for this, I will first define what is a skein. So as H-color skein, gamma in three cobordism, it is an embedding of the frame embedding of circles and intervals. Okay, such that the embedded intervals, their endpoints are in the arc. Okay, so here you have the endpoints of the embedded intervals. You also have circle components. Okay, framing, it means that you have a little thickening all of this. It is not just strands. It is ribbons, okay? And then the second condition requiring that the framing is vertical at the arc. It means that if you have a ribbon, the ribbon will arrive like this at the arc, okay? Cut at the arc transversally. And H-colored means that each connected component is labeled by some finite dimensional H module, okay? Like in Reshetikhin-Turaev ribbon graph invariant, the same kind of stuff. So these are more or less ribbon graphs embedded in three manifolds, okay? And yeah, we allow coupons. So coupons, it is exactly like in Reshetikhin-Turaev formalism. You can have little boxes labeled by H-linear maps. And of course, the H-linear map by which you label has to be compatible with the label of ingoing and outgoing strands. Okay, so this is for a skein. And now let's see what is a stated skein. So it's a state will be an element which is associated to what happens in the boundary. Okay, so look at this example here. So here you have a neighborhood of the arc. Okay, and then of course when you look at neighborhood of the arc, what you see is that some strands which are arriving and other which are going into the surface. Okay, so here you have outgoing, ingoing, outgoing. You have also colors x1, x2, x3. Then a state will be an element in this space. So here you have x1 outgoing, so it gives you x1. Here you have x2 ingoing, so you have x2 dual, and x3 outgoing, so you have x3. Okay, so a state will be an element of this vector space here. Because H is a Hopf algebra, I forgot to say H is a ribbon of algebra. So because H is a Hopf algebra, this is again a H module because you can use coproduct and antipode to act on such spaces. And a stated skein then is just a pair of a skein and a state. Okay, so in this example, you see what you have here is something which is ingoing, and if you follow the arrow, here you are outgoing, so you are in X dual and so on. Okay, yeah, maybe a comment. So here for the state, you don't need to don't search a physical relevance to the word state. Okay, it's just a word like another, and just a comment also. Maybe some of you have seen this construction for quantum SL2, and then if for H you take a quantum SL2, Then in this case, actually, you can color everything with the fundamental representation, C2, okay? And C2 as basis, as a two-dimensional basis. So you can call the basis vectors V minus and V plus. And then in this case, the states are just signs, okay? You just put plus or minus for states. Also, since C2 is self-dual, you can forget orientation, okay? So this definition, in the case H is UQ of SL2, reduces to the ordinary stated skein space introduced by Lě for surfaces and by Costantino and Lě for three manifolds. Okay, so this is just a generalization of this. Yeah. Okay, so now we have to put relations among this. So to put relations, we will use the Reshetikhin-Turaev functor. So recall that H is a ribbon of algebra, which means that H mod, the representation category, is a ribbon category. And then for such categories, you have a Reshetikhin-Turaev functor, which takes a ribbon graph and which gives a linear map, actually a H linear map, between certain vector spaces. So here, if you consider this example, again, the resulting map will depend on what happens on the left side and right side, depending on the orientation of the strands, okay? So you can see that on the left side, you see x1 outgoing, x2 ingoing, and x3 outgoing. So it will give you this source vector space. And on the right side, on the arrival, what you see is x5 outgoing and x1 ingoing, so it will give you this vector space, okay? And here I have put an example with a coupon. So you see you have a small box, which is labeled by an H linear map, whose source and target depend on the color of the strands.
Do you need anywhere that you have a Hopf algebra?
Yeah, for Reshetikhin-Turaev functor, you need. Or you need ribbon category.
For the states.
For the state, you will need.
You need the fiber functor, right?
Your question is why I choose H mod?
Yes, rather than an arbitrary ribbon category.
For the states, because I need vector spaces to say a state is a vector in this space.
Your ribbon category just needs to be fibered over vector. Like
I think you can do this, but this is a generalization on which François is working. Okay, and then we can use this to make the definition of a stated skein space. So recall that for our three cobordism, they carry an arc in their side boundary, okay? And then we consider the vector space over the ground field K, which is fixed from the beginning, which is formally spanned by stated skeins, okay? So you look at formal linear combination of pairs, gamma and S, stated skeins, okay? And you put some relations, and the relations are given by Reshetikhin-Turaev functor in the neighborhood of the boundary arc, okay? So here, if you are in the neighborhood of the boundary arc like this, then in general you will see some strands arriving, and close to the boundary you can have some interaction between these strands, maybe a crossing, maybe some twist, etc. Okay, and then also you have a state S, and you say, okay, I can erase this ribbon graph, but then I have to change the state. I have to change S with the state where you use the linear map associated to G by Reshetikhin-Turaev to act on S. Okay, and this makes sense by definition of the state because the state will be exactly in the target space of Reshetikhin-Turaev of G. Okay, and here you will have a state which is exactly on the target of the Reshetikhin-Turaev of G, which is here, okay, and then which correspond to these strands. And there is also some ribbon relation telling that states are linear in some sense. You want states to be linear. I think there is an example to make this clearer. Yes. So if you look at this example, for instance, you can draw this little box, okay, which is a cube neighborhood of the arc. And then the ribbon graph that you see in this little box is this, okay. So here you will get an endomorphism because source and target have the same strands. Okay, this will give you then this linear map, and you can act by this linear map on your state, and then you will get a new skein with a new state where this box has disappeared. Okay, actually you can go further here because you can also use isotopy. So we have to realize that actually the skein relations that they are not local. They are not only something near the boundary because you can use isotopy to bring your strands near the boundary and force relation. Okay, so here I can use isotopy to bring this crossing near the boundary and force a new relation, and then this crossing would disappear. Okay, so because of isotopy, the relations are not local. You can force relations by bringing stuff near the boundary.
Why it disappeared? It's not identity, right? This morphism.
Which one?
No, why have this relation again? Somehow this box disappeared.
But the state has changed now.
Huh?
The state has changed.
The state is changed.
Yes.
Okay.
So when you want to erase something, the price to pay is that the state changes.
State is like that.
Yeah. It's the point. And again, here also, if you bring this crossing near the boundary, the state will again change. Other questions? Okay, so these are the vector spaces that we assign to three cobordisms. And now let's see their algebraic structure. So they carry a natural algebraic structure. So if you have a cobordism M from two surfaces, sigma 1 and sigma 2, and another cobordism N to sigma 2 to sigma 3, then you can do composition, right? Composition is just gluing along a common surface. And then, or at the level of skeins, you have a natural operation which is stacking. So you see if you have a skein in N, and if you have a stated skein in N and a stated skein in M, then you can produce a new stated skein in the composition of the two, because you have natural inclusion of N into the composition and of M into the composition. And then you can just take this disjoint union of the two stated skeins. And for the states, you just do tensor product. And this is readily seen to be an associative operation, okay, which we call stacking. So here is an example. So here, for instance, you have a skein in a cobordism from sigma 1 to sigma 1. Here you have a skein from a cobordism to the disk to sigma 1. Okay. Then by doing the composition means that you identify the yellow part. Okay. And you see that when you do this identification, you get this skein. Okay. And by the relation, actually, the skein labeled by Y can now disappear, because by isotopy, I can bring it very, very close to the boundary R, and I can use the relation. So actually, in the result, the skein labeled by Y could be erased. But the state would change, of course. And this implies, so this very simple observation implies important facts, which is that if I define SH of sigma to be the static space of the cylinder for sigma, then this is an associative algebra. The stacking gives you an associative product. The unit element is just the empty skein. And if you have a cobordism between two surfaces, sigma 1 and sigma 2, then by stacking, you get a bimodule structure. Okay? So this construction gives you algebras and bimodules. Moreover, you have H equivariants, because you see that H act on states, because we say states are elements of a H module, because when you have two H modules, their tensor product is again an H module, and the dual is also again an H module. So it means that since the states belong to tensor product of H modules and their dual, a state is actually again an element of an H module, and then you can act on states. This makes sense, okay? And then you say, okay, the action of an element of the ribbon of the ribbon of algebra H on a stated skein is just the action of the states. And in this way, SH of M becomes a H module. Just a remark, the action is locally finite, meaning that every element has finite orbit, because the states are elements of finite dimensional H module by definition. So the action is locally finite. And it is very readily seen that you have this equivariance property, okay, which means that action of H is compatible with stacking. And here I use the Swidler notation for coproduct. So in your algebra, you have the coproduct delta, which is mapped from H to H tensor H. Okay, H tensor H. And since we don't want sum everywhere, we use this Swidler notation. Okay. And you have this equivariance property. And say differently, it means that you get actually algebras and bimodules internal to the category H1. And if you don't know what internal to H1 means, you can take this as a definition. Okay, so now we have quite an idea of what will be the target category of our functor. So you get algebras and bimodules internal to H mod. Okay, so it means that actually you land in this category BIM H. So the objects are associative algebras internal to H mod. The morphism are isomorphism classes of bimodules in H mod. The composition is the usual composition of bimodules, which is by tensoring over middle algebra. And the monoidal product is a sort product of algebras and bimodules. So this uses property of the category H mod. Since H is quasi-triangular, which means you have R matrix, H mod is braided category, and then you can define tensor product of algebras and bimodules. Okay, so for instance, if you have two algebras, A and A prime, you want to define multiplication on A tensor A prime, but you see the braiding allows you to switch the factor, the two middle factors here, and then after you can multiply. And you can do the same thing for bimodules. If you have two bimodules, you will get a tensor product bimodule over the tensor product of the algebras. And here it is easy. Again, you just need braiding to switch the two factors. So this way you get a monoidal category. And the first theorem is the following. So the stated skein operation can be seen as a strict monoidal functor from the category of cobordism with arcs to this category of bimodules. So for the functor part, it was a Costantino and Lďe, and we proved the monoidal part. And functor means this, and monoidal means this. Okay. So these are equalities of bimodules. Yeah, so what about the braiding? Maybe a bit faster here. Yeah, so there is an operation of 3 cobs that we have not discussed yet, which is the braiding. Okay. So what can we say about the braiding? How does the stated skein functor interact with the braiding? So to answer this question, we need to introduce this object, the Cohen, which has already appeared many times in talk, so I will not give more details. But there are 2 important properties. This object is the Hopf algebra in the category, and there is also a canonical of braiding on it, which is defined by this universal property. Yeah. And because of these 2 operations, you have this definition of quantum moment map. So if you have A an algebra in H mod as before, then a quantum moment map for A is an algebra morphism from the Cohen to A, which satisfies this commutative diagram. Okay, so here you see you have this sigma, which is used to switch the factor, and then basically it is a commutation relation between the image of this morphism and elements of A. Okay, because you see here you switch and then you multiply. So it's commutation relation. I don't have time to make it explicit in terms of H mod, but it is just some algebra morphism satisfying commutation relation. And what is interesting?
If you take both picture, would it be like full center, or
What in which sense?
like if you take a not coent and if you dualize everything on those arrows in your previous picture?
For end, I think you can still define the. I think you can still define the sigma by reversing all the arrows in the diagram. But then I don't know if quantum moment map.
Trying to understand the meaning of this.
There is another definition.
Maybe call it quantum moment map, or can you say something more about this?
There is another definition of quantum moment map which is easier to understand. So I can explain at the end if you want. Okay? Because this is the categorical definition, but this is an older definition which is easier to understand. I can explain at the end if you want, but I will just be short here, just to explain why this appears. Okay, this is because thanks to this quantum moment map, you can define a subcategory of BIM H, where now the objects will be pairs. So you have algebra and you have quantum moment map for this algebra. Okay, and you see since the quantum moment map is a morphism from the coend to the bimodule. A bimodule becomes a bimodule over the coend also. And then you can require some compatibility condition, which is this one. Okay, so you see it is the same diagram as for quantum moment map, but now it is compatibility condition because you use action instead of multiplication. And you can make a subcategory, which are this object and this morphism. And what we proved is that then this subcategory is braided because you can use these quantum moment maps to define a braiding. So now you have to remember that the braiding here will be bimodules. Okay, so what does it mean? It means that you have a bimodule which has to be a morphism in the category BIM. Okay, in the category of bimodules, you want morphisms like this. We have A1 and A2 are algebras. Okay, and by definition, this has to be A2 tensor A1, A1 tensor A2 bimodule. So here the braiding is really a bimodule. Okay, and actually as a vector space, this bimodule is just A2 tensor A1. And then on the left, you will just use the multiplication of this algebra. And on the right, here you will use, you see this is not in the good way. You have A1 tensor A2 and you want to act on A2 tensor A1. And then you will use the quantum moment map to switch the factor. So here you use the quantum moment map. And in this way, you can define a braiding on this category.
Let's say I start with a ribbon category, which is vect.
H is equal to C. I mean,
okay, so this is
effective, you see nothing there. Quantum moment
so
map.
in case of vector, it gives nothing.
You see nothing.
And can you give some simple example? Take simplest ribbon of algebra you have in mind.
But you want an example of such bimodules? Then
Yeah, this braided modular category. This beam QMM.
You want example of QMM?
Yeah,
Yeah, okay.
QMM, yeah, of course.
Look, you look at this. The internal and object, okay, which is V tensor V dual. This is algebra in the category, right? Yeah. So this is algebra, and you have QMM for this. So the coend as a vector space, it is H star. Assume H is fin dimensional, okay? And then you can do this. Then you want this. Okay. To a linear form, you want to associate function on V. Okay. And you do this. So this has to be function on V. Okay. So evaluation of V will be this. It will be you do this. You apply it to the monodromy matrix. This is element of H, okay? And then you act on V. This is quantum moment map for internal and. This example.
So in your category, objects are what? Are algebras equipped with such?
In this category,
Quantum
BIM QM, yes.
So the objects are algebras.
Pairs, algebras and QM.
And QM.
And QM.
QM is like a structure. Like
Yes.
a
Yes.
given algebra might have many of them.
Yes.
It's like, okay.
Yes.
So it's just example of objects.
Yes.
Okay.
This is an object in this category. And if you want morphisms in this category, it's easy. You just take internal obs. These are bimodules in this category. Because you can act on this and on this by these ones.
I also found them super confusing for a long time. So if you think of the stated skein algebra structure as coming from the action of some disk on your surface, then the quantum moment maps, a good way to get them is by acting by the annulus instead. The same
What?
An annulus instead, the same boundary can come in. And this is like a good source of that. That's what it makes sense. The boundary.
Okay. Yeah, and then so the theorem that we have seen before can be improved. So now with this braiding that we have defined, thanks to the QMM, we have actually, you see, restricted the target category because SH actually takes values in this subcategory equipped with QMM.
SH was what?
The stated skein functor.
A functor.
Yeah, the stated skein functor, and it is a braided strict modular functor. So with this braiding, it is the braiding corresponding to topology. Okay, and here you have the picture defining the quantum moment map on stated skein algebras. Time is over, so I will just fast. Yeah, just a few words on relation with the Kerler-Lyubashenko TQFT. So Marco will explain all of this, but there is this theorem which tells you that actually you have presentation by generators and relation for this category 3Com. Okay, the generated object is just the torus, because if you remember, objects in our category are just surfaces with one boundary component. but this is just genus, right? So the genus G surface is isomorphic to G copies of the torus. So this is your generating object, and you have generating morphisms, which come from the fact that T actually is of algebra object in this category of cobordisms. Okay, and moreover, you have certain special morphisms, so integral, co-integral, as Anna explained, and also other morphisms. So you have this morphism. You have morphism coming from the data, okay, product, co-product. So here, for instance, you have the product, you have the unit, you have co-unit, etc. Okay, and you have also extra morphism, integral, co-integral, and again, and also extra morphism. And you have list of relation. And this is presentation by generator and relation for this category. This is due to all these people, and this is well explained in paper by Bobcheva, Beliakova, Dorenzi, and Pierre Galini. And it means that a braided monoidal functor out to this category in any category C is just the same thing as the Hopf algebra in C, equipped with morphism, because you will say, okay, T maps to this Hopf algebra, and this morphism lambda, W, and tau, that they map to certain morphisms that you give. Okay, so you have complete classification of TQFTs out of this category. And in particular, you have the Kerler-Lyubashenko TQFT, which says, okay, if you have C which is reborn and also factorizable, which is non-degeneracy condition, then you get a TQFT by mapping T to the coent. So this is a modern point of view of the Kerler-Lyubashenko TQFT. And then the relation with us is as follows. So you have this square diagram. So you see at the top you have Kerler-Lyubashenko TQFT, at the bottom you have stated skein functor. On the left column, you have a forget functor, because for Kerler-Lyubashenko, you need cobordisms with more structure, okay, with extra data. And on the right, it is interesting. On the right, you have a very stupid functor, which I have actually started to explain here. So you see to any object in H mod, you can associate internal and, which is an algebra with QMM, okay? And to any morphism between V and W, any morphism, you associate the same bimodule. And this bimodule is exactly this internal point. Okay, so you see, you forget a lot of information here, because all morphisms go to the same stuff. And so it means that to any surface as algebras, you have this, okay, because T tensor G goes to L tensor G by Kerler-Lyubashenko, and then by the vertical arrow, you go to the internal and. And for bimodules, it means that for cobordisms, it means that for any cobordism between two surfaces, the stated skein space of the cobordism as a bimodule, it is actually just an internal on. So when H is factorizable, which is this non-degeneracy condition, and finite dimensional also, actually you see the stated skein bimodule does not see the topology of the cobordism actually. Whatever cobordism you take, you get at the end the same bimodule. Yeah. And yeah, there was some point of the proof, but yeah, my point of the proof may be this isomorphism between stated skein space of surface and then the morphism of the cohen. It is deduced from something which is called Alexeyev isomorphism, and which comes from the theory of quantum character varieties. And then then you can deduce that any bimodule is a sum of this kind of bimodule, because these algebras are very rigid. These are matrix algebra, right? And then by topological argument, you count dimension, and you show that actually this direct sum here disappears. There is just one submap. And I will stop. Thank you.
Any questions?
For structure, your cobordism also state arcs and so on, but at the end it doesn't see any topology.
No, it does not see the topology. When it is factorizable only. This is very a result in the factorizable case.
But you need factorizable if you're
For Kerler-Lyubashenko, yes. But for stated skein, you don't need. You can do stated skein for any ribbon of algebra. So you have more stated skein functor than Kerler-Lyubashenko functor.
So do you have any results that it's more interesting if you're not factorizable?
It's hard to compute, so it's hard to transfer, of course, especially the bimodule structure. Maybe the case where it is easier to see it is when it is finite dimensional, because here you have basis of the cobordism. Maybe finite dimensional and not factorizable. Here it can be interesting, but not factorizable. Because if it is factorizable, you lose all the information.
I still have a question about this. I want to understand this bimodules. If you take, say, H just a Swidler-Hopf algebra, can you kind of describe this category? Like, I mean, is it finite, many objects, or many simples? Is it abelian? Is it abelian, by the way? Or no, it's not really. Right?
No, because
It's Morita kind of category, right?
Yes, it's Morita category.
But like for Swidler, can you say something? It's nice Riemann-Hopf algebra.
Do you have classification for algebras internal to Swidler? Yes. See,
Maybe it's not a class, or because you ask conditions, right? You ask this. You say basically any algebra, it's object any algebra with this quantum moment map.
yeah, but if you forget the quantum moment map, just the target category is just all algebras in H-mod, okay?
Yeah.
And all bimodules internal to H-mod.
Yeah, okay.
But even for Swidler, I don't know what are algebras internal to Swidler.
Oh, well, we don't know what are algebras even in vect, right?
Sure.
Yeah, okay.
No, but I think
it's big category,
you
right?
can do examples. Yeah. But then for the quantum moment map, in the factorizable case, maybe a comment. In the factorizable case, it reduces to a much older notion, which is due to Varanuro and Vassero and Lue also. So when H is factorizable, a quantum moment map is just an algebra morphism from H to A. So here it is really H, it's not the Cohen, and satisfying this condition. If you take an element in A and you multiply by mu H, then you must have this. So A is an algebra in H, okay, so I can act on elements of A, and you have this condition. And you see this condition, it can be rewritten in this way. Probably with a mistake, but let's say this. Okay, probably this one. By using an antipode axiom. So you see a quantum moment map, it is just a map which entirely characterizes the action of H on your algebra.
Internally.
And you see, if you know the quantum moment map and the multiplication in A, then you can recover the action. So this is the initial definition of quantum moment map. It is a map, it is an algebra morphism which entirely characterizes the action of H on your algebra. And when H is factorizable, this definition is equivalent to Safronov definition. So you can imagine it this way. It is a map which entirely characterizes the action of H.
Does it make sense to restrict just to some class of A's, like simple algebras? Or you want all algebras?
For our category? No, all algebras. But again, when it is factorizable, you can restrict to simple if you want, because you learned in matrix algebras. See. So for factorizable, you can restrict the category to simple algebras. This is exactly what this theorem means actually.
I see. So even the image will be just simple algebras.
Yeah, just a vector actually.
Can you maybe, because bimodules would naturally want to be a true category, right? So can you somehow enlarge this framework, and this might see something more, because you still take ISO classes of bimodules.
Yeah, so this is a point. So this is what I was discussing during lunch with Christophe and Lucas. Yeah, so maybe the point is that you have to consider two categories.
Yeah.
Right. So you take object algebras, morphism bimodules, and two morphism, isomorphism of bimodules. And then I think this functor extends to these two categories. And then at the source, you have to take surfaces, cobordisms, and diffeomorphisms of cobordism. And most probably this functor extends to this. Yes.
Could you maybe go even further, and instead of just diffeomorphisms, take bordisms over bordisms, so some form manifolds with corners, and
this I don't know.
Good dream for
that. Dream.
I just want to make a comment. Your question, Azat, is basically asking whether we know a classification of the module categories over the suite representations.
Yeah.
The answer is not. I mean,
What,
no,
so
Shimizu's
simple one,
word-
exact ones we know.
okay,
Exact ones we
so
know.
for Sweetler.
Procedure, yes.
Okay.
Ask Martin.
Okay, great.
Yeah, yeah. Even for
So-
more complicated, even for small quantum groups, you know.
Yeah, that's Shimizu's, for instance.
No, but first was Martin.
Okay. Right.
Okay. Are there other questions? Okay, thank you, Matthieu. See you tomorrow.